A very good morning to all of you, and uh, I suppose everybody is fine right now, and everybody has a mood to learn something. And today will be our point of contention is basically to realize the very conventional equation that we use in quantum mechanics, and we call this equation as eigenvalue equation. And in order to interpret this equation, I would again try to take the help of those characters which are living in our Hilbert space. And in this Hilbert space, we have infinite possibilities, we have infinite geometries, and we have infinite vectors. And we can as well localize this Hilbert space. You can have a Hilbert space with three dimensions. You can have a Hilbert space with n dimensions, right? So this is it. This is what we have right now. And what I choose this operator as a character. This operator is living in this Hilbert space. And this operator is capable of bringing the change. Now, what does it mean that this operator is capable of bringing the change is, suppose there is a shape, the operator has the tendency that it can twist the shape. The operator has the tendency that it can compress the shape. It has a tendency to stretch the geometry. So it has a tendency to bring any kind of change. It has a tendency to bring any sort of change in the vectors that are living in this Hilbert space. And this operator, it interacts, it's able to find a vector in this Hilbert space, and it talks to this Hilbert space and tells him that I want to touch you. We understand when an operator will touch, it will subject that vector to change. Now this is a special vector. It tells him, come on, you can touch me. Not only you can touch me, you can pass through me. And the operator decides that I will touch this vector. Now when the operator touches this special vector, the vector does not change. The vector does not change. And a strange thing happens. The magnitude of the vector either increases or decreases by virtue of a number. Are you getting my point? You have an operator, it's capable of doing everything in the Hilbert space. It can change every vector in the Hilbert space. It encounters a vector that tells him, come on, you can touch me. The operator touches, it acts, it operates on this vector. The vector does not change. Instead, it comes up with numbers, either the increasing numbers or the decreasing numbers. Now this vector, which has not changed, this vector is called as eigenvector. Are you getting my point? This vector is called eigenvector. And the number and the number that's associated with this vector, that number is called eigenvalue. That number is called eigenvalue. And this is true even if your operator acts on a range of such vectors. And when it acts on a range of such vectors, you can have a range of these eigenvalues. And corresponding to each eigenvalue, you will have an eigenvector. Now, what do you mean by eigenvector? The eigenvector is a vector living in the Hilbert space when subjected by an operator and the vector does not change. This vector is what is genuinely called as eigenvector. Otherwise, all vectors which are there, we call them state vectors, right? And you have some special vectors living in this Hilbert space who are capable of not changing. Now, what does that mean? Can I illustrate that? For the sake of argument, if I assume something like this is only for the sake of argument, because Hilbert space has the minimum dimensions of 3. Okay? So this is just for the sake of argument. Now suppose we have a space like this, a vector space, and in this space there are vectors living, say zeta 1. Another vector is zeta 2. Here is another vector, say zeta 3. Here is another vector, zeta 4. Here is another vector, zeta 5. Here is another vector, 5, 1. Another vector, 5, 2, and so on and so forth. Right? And it has a shape like this. Say, for example, it's a square shape. Right? And what am I doing? I'm using an operator. Now, my operator is a stretching operator. An operator which will stretch it. Okay? Okay? An operator that will stretch. So when I will use this operator, say for example, I use it in this direction. Right? Now when I use this in this direction, what will be the result? So what I have done basically, I have stretched it. Oh no, it's bad. I have stretched it like this. Okay? And most of the vectors, they change it, but you see the impact is in this direction. And those vectors which were lying here, what was that? Did you note down that? That was, I don't remember, suppose it was zeta 3 and it was zeta 4. They will go along the action of your operator. The rest of the vectors, they will not. They may change their directions into some other forms. But these vectors, they will stay along their original dimension, along their original domain. So such vectors which align themselves along the direction of the operator, we call such vectors as eigenvectors. Now, the operator is asking the question. The operator is asking question to this vector. He's telling him, come on, why didn't you change? I have acted on you. I have acted on many vectors in this vector space. Most of the vectors have changed their domains. Some of the vectors tilted, some of the vectors rotated, some of the vectors twisted, some of the vectors reversed back. Why you didn't tilt? Why you didn't turn? What could be the answer of the eigenvector? What could be the answer of the eigenvector? And what should be the answer of the eigenvector? Come on. The eigenvector replies and tells the operator, come on operator, I'm like you. I'm like you. You can pass through me. We have a match. I felt that I should go with you because you are like me. And this is what gives birth to this eigenvalue equation. Is this clear? Okay, so this diagram should not be taken as the final diagram of anything. It's just for the sake of understanding that what it means to have the eigenvalues. So what we have, we have an operator, right? So we have an operator, and let me choose an operator. Say we have an operator, and I call this operator as a cap. Okay? And I have an eigenvector. And let me call this eigenvector as ket of zeta. Right? Now, this operator is acting on zeta, and from here we get a number and the same zeta. Right? You see, the vector has not changed. Your operator has either increased the magnitude of your vector, or it has decreased the magnitude of your vector. Is this clear? Are you getting this? Any queries? So you have an operator, and this operator is acting on the state zeta, which we call as eigenvector, because you get the same vector back multiplied by a scalar. So this operator is basically scaling up the eigenvector. Either it is scaling up the eigenvector, or it is scaling down the. You can think in terms of compressing that diagram, that domain I tried to explain, right? Is this clear? Okay. So what can we expect now? So this is our situation. Now, if I generalize this equation, I have an operator A acting on zeta I, and from this I obtain lambda I and zeta I. Right? Now, for lambdas, suppose I obtain lambda 1, lambda 2, lambda 3, lambda 4, and so on and so forth, lambda n. Now see, if you go to lambda n, your Hilbert space has n dimensions. If n is only 3, your Hilbert space has only 3 dimensions. Are you getting my point? So what's happening? These are lambdas. Now corresponding to each lambda, what you will have? You will have a corresponding eigenvector. So you will have zeta 1. Okay? You will have zeta 2. you will have zeta 3, and so on and so forth, you will have zeta n. Now this kind of combination, when you obtain by resolving this equation, we call this non-degenerate. Non-degenerate. What we call it? We call it non-degenerate. So for non-degenerate, corresponding to each eigenvalue, you have one eigenvector. Is this clear? We don't have to discuss non-degenerate, degenerate, at least in this class. In quantum second, you will have to go through these theories in the framework of perturbation. But here, at least we have an idea that what non-degenerate means. Okay? Now, if I'm solving, I obtain lambda, and I obtain lambda 1. And corresponding to this lambda, I have zeta. I should call this 1, I should call this 1, I should call this 2, so that it resonates with the vectors. So this is zeta 1, okay? Now this is what? No, this is zeta 2, and this is zeta 3. Now, what is different in this case? In this case, you have two eigenvalues which are same. Okay? But to each eigenvalue, you have a different eigenvector. Right? What will I call this? Yeah, what will I call it? We call it doubly degenerate. Okay? Double degenerate. This is double degenerate. And if you have lambda, and you have zeta 1, zeta 2, zeta 3, zeta 4, zeta 5, then this whole thing is degenerate. Are you getting my point? You can even differentiate whether your system is doubly degenerate, triple degenerate, quadruple degenerate, depending on the number of these lambdas which are same. Right? Clear? Right? Okay. So, another important thing, so this was an idea about the eigenvalue equation. I think I'm able to cross the point. Now, if I have an operator A, this operator is acting on zeta, and from this I obtain phi. Right? Here I'm just trying to talk about the inner product. So you have an operator A, it's acting on zeta, and from there we get phi. And if I define another bra of psi living in the same Hilbert space, living in the same vector space, then the inner product that I will take between this psi and phi will be equal to what? Okay, for psi is psi, isn't it? For phi, I can write a cap zeta. Right? Now, in this case, I can write like this: psi a phi is equal to psi a phi. There's no difference between the two. Either your operator first acts on phi and then on psi, or your operator acts first on psi and then on phi. The result will be same. This is how the inner product is defined here. Now these operators have to be linear. The operators that we have been talking about, they have to be linear. They have to be linear. They have to be linear operators. What does that mean? That means if I have a scalar and I multiply it with some bracketed A1, why should I put a number here? Some bracketed say zeta 1 plus zeta 2. So if I can distribute this alpha linearly with both the vectors, then assuming this alpha to be an operator, okay, I choose alpha as an operator, it acts on this bracketed term and we obtain alpha zeta 1 plus, this is an operator, alpha zeta 2. So it should hold this kind of property. If it holds the distributive property of the operators, then you have the linearity in operators. The operators that you are choosing in your framework, they have to be linear operators. They don't have to be the non-linear operators. They will not work in this framework. Right? Okay. Now, see, when we go to the actual systems, like, let's go back to the classical physics. What we have in classical physics? In classical physics, we can completely measure. We have observables in classical physics. What are these observables? The measurement of position, the measurement of momentum, the measurement of kinetic energy, the measurement of potential energy, the measurement of pulse, impulse, velocity, acceleration. So in classical physics, we have observables. Corresponding to those observables in quantum mechanics, what we have? We have operators. So, if you have an observable in classical physics as position, in quantum mechanics, we don't have anything like position. What we have a position operator that will act on the eigenvector, that will act on a state vector, and you will come up with the position. In classical physics, we have momentum. It's a directly measurable physical quantity. It's an observable. Corresponding to this momentum, we have momentum operator in quantum mechanics. Corresponding to total energy in classical physics, we have the Hamiltonian operator in the quantum mechanics. Now this Hamiltonian can either be independent of time or it can be dependent of time. When it depends on time, it gives us the evolution of the system. When it does not depend on time, it gives us quantization. So the operators that we have here, these are not these generalized operators. We have some special operators which we have to deal with in this class, and we call them Hermitian operators. I think we will stop here, okay? Next time we will take on those operators. Any questions? Yes? So I thank you all for being the part of this class. So please, you can stop it.